Okay, I guess this should be clear to everyone how the TCP handoff works. I want to briefly describe a scheme that will also answer your question. What happens if you have a client that is actually going to push a lot of data to servers? This is a scheme that we implemented a few years ago. It is not widely used because, hey, we're a research institute, but variations of this theme are implemented elsewhere. Okay, so I'm going to give you this example because I actually think I understand it well. What is the basic idea? Just imagine that you have a huge collection of servers. No, one step back. One thing that you have to realize that if you want to use TCP handoff, that really doesn't scale across the internet for the very simple reason that people don't like you spoofing others' IP addresses. Okay? So it's generally confined to a single site, a single administrative unit. The scheme that I'm now going to describe actually can be implemented across the internet. And the trick is that you continuously try to fool the client. That's basically it, without the application really knowing it. And the idea is actually relatively simple. You have a collection of servers, and just assume that these servers are distributed across the internet. And what you're interested in is to have these servers operate behind one IP address. Okay? If you talk to this distributed server, you just want to have one IP address where you basically set up a connection to and then you start talking. That's the basic idea. And the whole idea is based on the fact that you have a service and the service is associated with a network address and a port. Okay? Now, the whole idea is that you in principle use mobile IP to solve your problem. And the scheme of how you use this is actually explained over here. What you do is you have this distributed server over here, which consists of a number of different machines. And each of these different machines have an access point. And every one of these access points is actually handled by a real IP address. And I don't care whether it's IP version 4 or IP version 6. We implemented it for IP version 6. The principle is exactly the same thing. Now, do you remember mobile IP? No. Okay. The principle of mobile IP is the following. You have a device that has a fixed address. That's the basic idea. Every device gets its own address. And you move from place to place to place. You as a client want to talk to that machine with that IP address. Okay? But the problem is you don't know where that IP address actually is. Now, in mobile IP, the principle is like this. There is something like a home server. You forward all your packets to the home server. The home server keeps track of where you are. And where you are is implemented as follows. I'm a device, I'm a mobile device with my fixed IP address. I come into a network. And I say, hey, here I am. Okay? Now that network has a representative with, of course, an IP address. And what that representative does, it says, okay, I will host you. And it records a binding between its IP address and your fixed IP address. And it forwards its IP address to the home server associated with you as a mobile device. Got it? Then you as a client, you go to the home server. That home server now knows the representative of the network where you're being hosted. It forwards the packet. The packet can then be forwarded to you. Everybody happy. And in the meantime, what happens is that a message is sent back to the client. Don't come to me, the home server. Go to that representative because that's actually where the device is. The beauty of this scheme is that it all takes place at the networking layer. Okay? If you're an application, you don't see this. You just use your standard IP address that you knew this device really has. And then there's a translation of that IP address to the representative of the network where your device is, your mobile device is, where it will then be handed off to that device. This is how you can actually implement a distributed server. Yes? It comes close to principles like in a NAT, in a network address table. But let me explain to you how it works the way that we actually implemented it. So here you have an application that talks TCP, and X is the address associated with this distributed server. Okay? Now what you do in mobile IP is you maintain bindings. It's not this address X, but you have registered a care of address of your mobile device. And that care of address is the same as the address of the representative I just talked about. Okay? So as soon as you have this binding, that means that the application will talk TCP, thinks it's talking to X, but in the mobile IP code in your local stack, the translation will be made like, oh no, it's not X, it's this care of address. And this is exactly this one. And from there on, you actually talk to that address, which is now just a normal IP version 4 or IP version 6 address, and your packets are forwarded to this point over here, which happens to belong to this physical server. Well, what's the beauty of this scheme? This thing is a direct connection. And by direct connection, I mean it's really this client talking to that server and no detours or anything like that. Only the first time. Because the first time, you do have to know what the care of address is. But once you have that, you have a local binding on your clients saying, X really means CA1. You don't see this as an application. It's in your network stack. And from that moment on, all your packets flow to CA1.
So they're no longer routed through the representative?
They're no longer... whoa. They're routed to this point, which, if this is a fixed server, is directly the address associated with that server. In the case of a mobile device, it will be the address of the representative of that mobile device in that network.
Okay.
Got it?
Yeah. So you get the address of the fixed server from the representative.
You get the address of the fixed server from the representative. You get the address of the fixed server from the representative. If you're a mobile device, yes.
Right.
Yes. Absolutely. You get the address. I'm thinking very hard. You as a client. Okay, let's roll back. There will be something like a home server, whether it's in the network or as a separate service on top of the network. I'll just skip that part. You get the address of the representative from that server. It will tell you this is where this mobile device is.
Yeah.
Got it? That information is forwarded to the client. And from that moment on, you'll have a one-on-one communication between the client and the actual server. And even if it's through the representative, that really doesn't matter because that's really local communication. Is the principle clear? I've just set up a distributed server. Because a client number 2 will say, hey, I think, I'm going to talk to X, but it will have a different binding, which translates to a care of address number 2, and its data will actually be forwarded to a different server. What is interesting about this thing is that this server may be physically closely located to this client, and this one will maybe situated across the internet, very far away, but physically close to this client. And now suddenly, they all are talking to the same address X, and everybody's happy. Yes?
Why don't we use
Why don't we use Anycast? Does anybody know what Anycast is? Anycast is essentially a single address for multiple servers, and basically in an Anycast addressing scheme, your packet is forwarded to the, I'll call it, closest server meeting that address. Why don't we use Anycast? Because you cannot use it for stateful communication.
It's not guaranteed that the next packet will go to the same server.
How would you guarantee that?
You cannot guarantee that.
No, that's not an answer. How would you guarantee that? That's what I asked. You say you can't. I say you can. What you could do is you could use Anycasting for initially locating a server, and then under the hood, you set up a fixed TCP connection to exactly that server. Under the hood. Otherwise, you're right, you can't. If you continue using the Anycast mode, it's not going to fly. Agreed. And then your answer is completely correct. And the answer was, you can't, one of the drawbacks is you can't have stateful servers because you have to go back to the server that you initially contacted. Very good. But I think there's a better reason why you can't use Anycast. Okay, but that's a matter of better versus worse. Okay? And I agree, if you don't use Anycast, you have more control of actually the server that you're going to select. But there may be actually a better reason why Anycast will not work in general. Yes? Because of the load balancing, could be. You're making a, I wouldn't say a mistake, but all of you are making a few assumptions that I'm not making. The closest is not the one with, okay, is that not the server that you want? Let's assume that all servers are identical. So let me translate your answer, which is correct. It doesn't scale. Okay? Suppose in an Anycast system, your server is not close by. Okay? That's basically also what you're saying. Whoa, now I got to hunt for it, right? That may be a bit difficult. I have to search, I have to continue Anycasting until I hit a server that actually fulfills my needs. Which translates to your answer like, my God, I have to set up a whole infrastructure to making sure that that address is actually routed to a server that I know. It's not undoable, but it may not scale very well. A counter question. How successful is multicasting at the network layer in internet? Yes, very good. As soon as it leaves one carrier network, it stops. And basically, you're telling me why. There's no business model. There's no reason why a multicast packet would travel the internet across all these different providers. They have no incentive to do this. Exactly the same with an Anycast address. Technically doable, but from an economical point of view, nobody's interested. And then the beauty of this scheme, or similar schemes, let me emphasize this, or similar schemes, is that you do put up a service somewhere at a fixed point, and that's where the translation takes place, where you get your binding information, and from there on, you blast away. I just gave you a centralized solution, right, to a simple problem. Because you do have to have this central point where you can actually set up the bindings. Okay? And that's, ooh, I like this question. In this setup, does the application have to be stateless? The application protocol have to be stateless. Does, in this setup, does the application protocol need to be stateless? First, give an example of an application protocol to make this more concrete.
Like HTTP or something. I mean,
HTTP is already stateless.
Some protocol you can make yourself.
Transaction? Is a transaction okay? Yeah. Okay. So a transaction works like, hey, let's start something, read, write, close transaction. Okay? Application level protocol. Not stateless, very stateful. You talk to that server, okay, because it has your data. Can that be done in this scheme? Why not? Hold it. I'm asking the questions. as you're giving an answer. Exactly. So basically, I'll repeat, don't worry. So basically, what you're saying is that why not? Because the binding between the address that I'm getting and the address that I think I'm talking to is fixed. It's set once, and I can keep it as long as it's valid. Let me put it that way. Which means that if I think I'm talking to X and it really is CA1, that's fine. You can do as much as you want. Okay? As long as the binding is valid. As soon as the binding turns out to be outdated or whatnot, then it fails. Yes? Sure. If it turns out that the server listening to CA1 fails, you're in trouble. So what you would want to do in these type of schemes is make sure that address can be taken over, or that you have the distributed servers collaborate in maintaining a reliable view on X. Okay? I'll say something about that in just a minute. Yes? Yes. So normally you would get, if you go to DNS, you would get different A records, for example, for Google. And you would be directed to different servers. Yeah. Yeah, exactly. So the same scheme of one layer up. Just a minute. Just to follow up this remark, like, hey, it's less fault tolerant. To give you an idea, we actually implemented a media server, a multimedia server, and what we did is we set up TCP connections using this scheme to separate servers, and we set it up in such a way that we deliberately killed servers, and then we wanted to see how quickly another server could take over the TCP connection. Well, if you do this right, and you notably handle the buffering that takes place in a TCP connection, meaning that when you are pumping data or getting data from one server, that you make sure that there's another server who has exactly the same TCP state, you can do a handoff from one server to the other in less than 10 milliseconds. That means that when you're looking at the screen, you see a hiccup. We did this over a wide area link. Hey, not bad, right? So the fault tolerance, yes, you are absolutely right, but hey, you can make a fault-tolerant distributed server if you apply the right techniques. Okay, you had a question. Is it the job of the home server to keep, I'll rephrase it a bit, the binding at the clients up to date? The answer is, in principle, yes. But you can delegate this to other servers, but in principle, yes. Okay? Let's move on. And this is basically what was on these other on the other slides. It's going into the details. Let me briefly talk about an example system called Planet Lab, and I think that's going to be, yes, that's going to be 2 more slides, and then we'll stop for today. How many of you are aware of Planet Lab? Nobody. Oh, you thought about it. Okay, that's at least that's the first step. Let me put it that way. Planet Lab is a really nifty system. I'll be discussing it briefly because it is a very practical way of building a wide area distributed system, or actually server, and it came out of necessity because we had all these researchers at a certain point doing research on wide area networks, but they didn't have a platform. You have to realize that, notably, systems researchers, we don't do a lot of theory. What we do is we run experiments, and we try to learn from our experiments. But if you don't have a platform where you can experiment with wide area systems, what then? No theory. So there was this guy, Larry Peterson, who actually came up with a very good idea. He said, why not build our own distributed server? And the model is very simple. What you do as an organization is donate 2 machines, 2 computers. basically powerful PCs. They don't have to be really powerful, but I think by now the requirements are something like 8 gigabytes of main memory and a decent CPU. You donate 2 machines, and once you've donated 2 machines, you're part of this Planet Lab system. If you have lots of organizations that donate 2 machines, then suddenly you have approximately 1,000 machines. And I can tell you, that's a nice way of actually playing with things. So Planet Lab consists of a bunch of approximately 1,000 PC-like systems distributed across the internet, and what you can do is try to grab machines to do wide area experiments. Now that's already nifty, but the really nifty part is if you want to build such a platform, you have to suddenly satisfy the requirements from many different organizations. And those requirements are, I'd like to have a machine like this. I'd like to have a machine like that. Okay, how do you do that? And that's where virtualization actually comes into play. And it's a very practical way of building a very large virtual distributed machine. So you have different organizations, they contribute machines, which they subsequently share for all kinds of experiments. And Planet Lab has been up and running for, I think about 10 years by now. So it's doing fairly well. Now, you need to ensure that the different distributed applications can actually run side by side on this platform. This calls for virtualization. And you really have to realize this is just a big distributed system, distributed server. Very much like how you would organize a website, okay? But now suddenly the application servers and database servers, they're now spread across the internet. And the question is, how do you do that? And the way that you do that is you take Linux and you run Linux on each of these machines and you modify it a bit. Okay, this is exactly what happened with Planet Lab. So when you donate a machine, what you do is, this is your machine, you have your Linux enhanced operating system, and on top of that you have so-called V servers. Now, I want you to think along with me. What you really need is the following. If you would run this system by yourself, you would have a bunch of machines, each running Linux, and having exactly the same Linux environment. Let's just keep it simple, right? And by environment, I mean things like you have the same Python libraries, the same C libraries, perhaps even the same version of Linux, all these type of things, so that you can have your application spread on these different machines and they all expect the same thing. Now the problem with Planet Lab is that indeed I may expect environment X, but my neighbor may want to have environment Y. That's one problem. Well, there's a very simple solution to that. Switching environments in a Unix system is actually kind of simple. Change root? Ever heard of the change root command? What the change root command does, it says, when you hunt for stuff, read libraries, start here. And it's different from a working directory because it basically sets your starting point for your tree in your file system. And that's where you put in your libraries. Okay, so that's the easy part. But there's something else. And this is really where the enhancement comes from. If I'm supposed to start my applications in a Linux environment, I assume that there's an init process, right, on that specific machine. And I'm not expecting that because I'm sharing my Linux environment that I don't know what this init process is. So what you need to do is you need to fiddle a bit with process IDs to give me, as a researcher running on Planet Lab on that specific machine, the idea that that machine is all mine. So I fiddle also a bit with process IDs, and now suddenly, when I'm using this machine running in this V server, I think it's me as the only user of that machine. And that's the only thing where the enhancement comes from. So this is basically how they played a bit with the Linux operating system, and they provide you the right Linux environment to run your stuff. That's as simple as this type of virtualization can actually get. No virtual machine other than an extremely simple way of faking a Linux environment, playing with some process IDs and using change root. So what you then get in the end is you try to grab machines, and once you have these bunch of machines, you virtually have a slice of V servers that are running on a bunch of different machines out there in the internet. And I can tell you, that's when the fun starts. Grabbing the machines turns out to be somewhat of a nasty business. Yes? So, let me phrase it like this. Can several users at the same time run their applications on the same physical machine without noticing this from each other? And the answer is yes. They may notice it in performance. They will not notice it in functionality. The environment that they are offered by a V server is an environment that you would get if you were the only one running on that machine. Yes? Yeah. So basically what it boils down to is that, I'll rephrase it a bit. If you would take a look at, first of all, is this unique functionality for Linux? No. I think they're called jails indeed in BSD, right? So, so it's completely isolated environments that give you the illusion of being the only user of that system. And the illusion consists of handing out the right process IDs, and there are also kinds of low-level things, but you are not aware of the fact that there may be somebody else working on that same machine as well. And it's actually a really cheap way of building a virtual machine. That's basically it. It's also very efficient. Yes? Interesting. Everybody's talking about fault tolerance. I thought security was the key word, actually. But I'll buy fault tolerance as well. Okay. The reasoning here is, would it be difficult to actually migrate processes from one machine to the other in the V server? My first inclination would be yes, difficult. Not undoable, but difficult. And that's because I think it will be difficult because I can't really imagine, let me try to rephrase this correctly. The virtualization is so basic that if you want to do true process migration, you will also have to migrate state that is not only maintained in the enhanced part of the operating system, but in the operating system itself. And that's where it's going to hurt. But I'm not entirely sure. So, okay, it really kind of depends on how you implement these enhancements. But let me get back to migrating processes next time, because migrating processes is really a nasty topic, and it's not being done that often anymore. Okay, last question?
Others are actually
Sure. Don't forget, so if you want to bind to something externally, if you want to have an external interface, you're in trouble with these machines. Answer is yes, but you can circumvent those problems. Okay, don't forget that any of these machines has a real address. If you want to have full flexibility, this technique is not going to work, and you will need the virtual machines that you see in the cloud.